Hi, in today's lecture I will be focusing on the step-by-step design of analog filters. A filter is usually designed in an analog world, but these analog filters have been extended towards the design of the digital filter. Why we design a filter? A filter is used to pass certain frequencies and block certain frequencies, and we have in the analog regime we have passive filters as well as active filters, while in the digital regime we have IIR filters as well as FIR filters. So for designing of the filter means that we have to calculate the transfer function of the filter, and from that transfer function of the filter we do the realization of the filter, and once we do the realization of the filter we are able to anticipate the actions of the filter. So with the help of transfer function we can also construct the circuit diagram of the filter. So for designing a filter in the analog world or in the digital world, we have to keep one thing into consideration, that the designers want to construct a filter which is lossless in the pass band where it is passing the frequencies, and has infinite loss in the cutoff band where it is attenuating the frequencies. And it is nearly impossible to construct such kind of filter because this is an ideal kind of filter. The approximate filters made by the humans, and the aim of the designer is to make as much lossless as the pass band in the filter design, or as much infinite loss as the in the cutoff band or in the attenuation band of the filter, and the designer is basically focused on those aspects in the practical situations. We have different ways to design a filter, an analog filter if I am talking about. For the design of analog filter we use various mathematical models, and those mathematical models, out of which four are very much popular. These are Butterworth model, Chebyshev model, elliptical model and Bessel model. All these models have their own mathematical models and the polynomials. We study over here the Butterworth model. We can see that in the chapter number 8 where we have studied that there was a circuit diagram of a low pass first order filter, and when we have calculated the transfer function of that filter it was like that. So if we take the amplitude of that transfer function or the impulse response of the filter, then it is kind of this arrangement over here, and we can replace over here n. It means that this is a kind of Butterworth model which can be used as a Butterworth polynomial to calculate any order filter transfer function. Sorry. So why we have preferred this Butterworth model is that its pass band has less ripples and the attenuation band also has less ripples, and it is for that reason is being said as a maximally flat filter, and the ripples are of the order of zero point 0.1 plus minus. We can calculate this Butterworth approximation in the linear units as well, or in the decibel units as well. And when we construct the Bode's plot of that Butterworth polynomial, then for a low pass filter it is showing these kinds of results over here, where we can see that in the pass band there are negligible or nearly no kind of ripples, and in the attenuation band as well. And there are different orders. The first order is less steeper, having less steeper roll off, while the second order has more steeper, and the third order has more steeper roll off. And this is the ideal response, this dotted line. And higher the order of the filter, the more it will be proceeding towards the ideal response of the filter. Now we can see how we design an analog filter by using the Butterworth approximation. For that we have to know some things, that for the design of the filter we need to know specifications of the filter for which we have to design that filter, and we always design a low pass prototype design. We always design a low pass filter, and by using the frequency approximation technique, we once get the transfer function of the low pass filter, we can use that frequency transformation to convert it into high pass, band pass or band reject filter transfer function. So what are the different specifications which we require in anticipation to design an analog filter by using the Butterworth polynomial? As we can see in the Bode's plot of the low pass filter over here, we have, this is the pass band gain, which is H1W. One thing is that we require, and second, this is H2W, this is the stop band gain, this second thing we required, and the third thing is W1, and the fourth thing is W2. W1 is the frequency till which the pass band stops, and W2 is the frequency from where the attenuation band starts. So these H1W, H2W, W1 and W2, these are the four things which we required in the specifications to calculate the transfer function of the filter by using the Butterworth model. So by which, by these four specifications which are also elaborated over here, we can able to calculate the N, which is the order of the filter, and WC, which is the cutoff frequency of the filter, and we can calculate the transfer function of the filter from this N and WC, and this transfer function can be used to construct the filter which is being said as the realization of the filter. And there are some other simple explanations about the four specifications which were required as previously told in this diagram for calculation of the transfer function of the filter. Now we can see how with the help of Butterworth polynomial we able to calculate the transfer function of the filter. Now you can see over here, the first step is to determine the N and WC with the help of Butterworth polynomial. In the Butterworth polynomial we put H1W and W1 over here like this, and H2W and W2. Here we have two equations, and we have only two unknown entities which are N and WC, and we can simultaneously solve these two equations to calculate N and WC, and we are able to calculate the N and WC. So in the second step we have to determine the poles of transfer function, and the poles of transfer function can be calculated by this formula, which gives us the number of Butterworth poles, as we have N, which was previously calculated as some, for example, value 2. Then we have number of Butterworth polynomials will be 2n is equal to 4, and these are the total Butterworth polynomials. And what are the these are the total 4 Butterworth poles, and what is the angle between these poles will be calculated by this formula. Theta is equal to 360 degree divided by 2n, and that angle will be 90 degree. So where would be the placement of the first pole? If the order of the filter is even, then the first pole will be placed at theta by 2, 45 degree, and if the order of the filter is odd, for example 3 or 5 or 1, then the first pole will be placed on the x-axis and the remaining poles will be at theta degree. So we can calculate with this formula 2n and theta the number of Butterworth poles and the angle between them, and based on the odd and even poles, odd and even order of the filter, we place the number of poles in the unit circle, and then we are done with this step, which is the determination of the poles of the HS. Now is the task is to determine the valid poles of HS. As we know in the theory of stability that in the S plane, as this is the S plane, the poles which are coming on the left hand side are the valid poles, and the poles which are coming on the right side are not valid and they are invalid poles. So we need only valid poles to calculate the transfer function of the filter. So in this diagram where we have placed by using these two formulas the poles over here in the unit circle, we see that we have only two poles which are on the left hand side. So these are the valid poles and we can use these poles to calculate the transfer function of the filter. So first, to calculate these poles will be with the help of this formula. This is a kind of Euler formula which is used to calculate the conjugate poles. As we over here we can see this and this is a conjugate pole, this and this is not a conjugate pole, this and this is the conjugate, and this are not conjugate poles. So conjugate poles are these, and we just change of sign in the Euler formula over here we can able to calculate these two poles, and we do the same over here and we determine the number of poles over here, the B1 and B2, and we have WC is equal to 1.5, and we have calculated the two valid poles over here. Now the fourth step is to have calculation of the transfer function, and this is a generic formula for the second order filter, and these are the unknown pole values which are represented by a plus jb and a minus jb. So we put the values of the two poles over here, and that's all, and just we have to put the value of WC over here. Now we have just simplified our transfer function, and this is all. This is a transfer function of an analog filter based on the Butterworth mathematical model. Now we can see another example. Here we have a Butterworth low pass filter. This is having the four specification values H1, H2, W1, W2. The first step is to determine the N and WC. We have the Butterworth formula. We have put H1, W1 and H2, W2, and we have simultaneously solved the two equations. First calculated the N. We have rounded it off it to 3, and then we have put this n value in any of the two equations, and we have calculated the value of WC. And then the second step is to determine the pole which are calculated by 2n. We have n is equal to 3, so we have 2n is equal to 6. These are the number of Butterworth poles. And then we have the theta calculation, which is 60 degree. As we have 3 and the order of the filter is odd, so the first pole will be placed on the x-axis and the remaining poles will come after a 60-degree angle in the unit circle, and after which we have calculated the valid poles, and the valid poles are the poles coming on the left hand side, and we have calculated this pole as well independently, and these two conjugate poles with the help of Euler formula. And over here we have done so, and the last step was to do the calculation of the transfer function. We know that for the second order filter it is this transfer function with two unknown poles, and we have for the first order filter it is this kind of transfer function. For the low pass filter these both are the for the low pass filter first order and second order, and we have to calculate the third order transfer function. So multiply these with each other, put the values of WC, put the values of two poles over here, and then we have got our transfer function for the third order filter. Now I will be doing a kind of slight comparison between the Butterworth filter as well Butterworth filter as well as the Chebyshev filter. In the Butterworth filter we have no ripples, while in the Chebyshev filter we have some ripples in the pass band as well as in the stop band, but the Chebyshev roll off is more steeper than the Butterworth, and we can say that higher order Butterworth filter is equal to lower order Chebyshev filter, because higher the Butterworth filter the more steeper its roll off would be. And we also rely on the Butterworth filter because it has no ripples in the pass band and the attenuation band. And the foremost important reason for neglecting the Chebyshev model and focusing on the Butterworth model is that the Chebyshev model is much more complex to calculate than the Butterworth model. Thank you very much.